So we're going to be continuing our study on kinetics. So just to review, we talked about how it takes time for a reaction to happen, right? And that's called the reaction rate. And then the step-by-step process is called the reaction mechanism. And the study of that is called kinetics. Just review from last time. We talked about how everything is just kind of determined by the amount of collisions. So the more collisions there are, the faster the rate. And it's affected by 4 different things: physical state, concentration, temperature, and if there's a catalyst or not. We talked about all this last time. We're going to skip some of these problems. You guys can take a look at it if you want, but we're going to go right to the calculation part. So key thing to remember is that reaction rates are determined or described as change in a time interval. So the unit of measurement for reaction rates is going to be molarity per second. Okay, molarity divided by second. Okay, and if you forgot what molarity is moles per liter. So basically, how much does the concentration, the molarity, change every second? That is the unit of measurement for reaction rates. Yeah, things are getting more complicated now. Okay, so I'll leave that up there, but we're going to be taking a look at this image right here. So just kind of take a look at it and try to understand what is going on. Okay, so inside this image, we have red balls that are compound A, and then we have blue balls, which are compound B. Okay, and we're going to assume that all of these containers are 1 liter, so the volume doesn't change. But if you guys notice, what happens to the concentration of compound A as time goes on? So the concentration of A, does it go up or down? Yeah, the concentration of A goes down, and these brackets are kind of a shorthand of saying concentration. And then the concentration of B goes up or down? Up, yeah. Okay, so that's basically what's going on in this image. And you can tell quantitatively with the numbers, you can see that. You start with 1 mole of A, goes down to 0.54, goes down to 0.3. Start with 0, go to 0.46, go to 0.7. Okay. Easy enough to understand, right? What's going on? Okay. Again, you guys don't need to copy everything down. We're just going to be solving the problems. It's all posted for you so you can follow along. Okay, so if you guys have this file open, just stay on this picture because that way you don't have to go back and forth. So stay on this picture, but I'm going to go down to the first problem for today. Okay. Now, for this picture, we can calculate 2 different rates. There are 2 rates that we can look at. We can look at the rate of how A disappears, or we can look at the rate for how B appears. Right? There's 2 different things that are going on. A is appearing and B is disappearing. Now, we can calculate something called the average rate, basically the average of how the concentration changes with this formula. Okay, so this triangle, if you guys remember, triangle always means change. So the change in the concentration divided by the change in the time. So this is probably the important formula that you're going to want to write down. Okay, so how does A change? The concentration of A change based on the change in time. And if you guys want the expanded formula, it's going to be the final concentration minus the initial concentration divided by the final time minus the initial time. Okay, and then you can obviously do the same thing for B. The concentration of B at the final time minus the initial time divided by final time and initial time. So that's how you calculate the average rate. Should be pretty familiar with the algebra for that already. Okay, so if you guys understand that formula, I'll give you guys about 2 minutes. I want you guys to solve 11.3. I want you to calculate the average rate at which A disappears from the time interval 0 to 40 seconds. Okay. Try to use this formula, and you're going to need that image that we had up earlier, so just make sure you have it up on your Chromebook. want you guys to calculate the average rate of A's disappearance from 0 to 40 seconds. I'll give you guys about 2 minutes to try that out. Okay, maybe another 40 seconds to finish this up. Alrighty, guys. So if you guys are finishing up, feel free to finish up on your own, but I'm going to start going over how to solve this. Okay, so what we're going to want to do is we're going to want to find the concentration of A at the final time and the initial time, right? Because we want to plug in everything into this formula. We already know that the final time is going to be 40 seconds, right? And then the initial time is 0 seconds. Okay, and we're going to be subtracting that. So the bottom of the fraction will be 40 minus 0, so it's just going to be 40. I almost said 0. Okay, so what's important to us is the concentration of A at the final time at 40 seconds and the concentration of A at the initial time, which is 0 seconds. So we're just going to go back up to the picture. And so we're going to want to find the final concentration of A, which is at 40 seconds. So I'm going to just denote it like this. And then the concentration of A at 0 seconds. Okay. So let's take a look at this. We know that concentration is molarity, right? Moles divided by liters. So if you look at 40 seconds, the moles, we have 0.3 moles of A. So that means the molarity of A at 40 seconds is 0.3 divided by 1, which is 0.3, right? So the final concentration is 0.3 molarity. Okay. And at the beginning, at 0 seconds, it's going to be 1 mole divided by 1 liter. So it's going to be 1 molarity. Okay, so the final molarity of A will be 0.3 molarity and the initial will be 1 molarity. Okay, make sense? So if we use our formula, we just need to plug this in. So let me go down a little bit. Does it fit? Yes. Okay, it fits. Actually, it kind of doesn't. Dang it. Okay. So what we're going to do is we're just going to plug things in right here. So we know that the average rate, so the rate average, is going to equal the final concentration, which we said was 0.3 molarity. So 0.3 molarity minus the initial molarity, which is 1. So 0.3 molarity minus 1 molarity. And then we said the final time is 40 seconds minus the initial time, which is 0 seconds. Okay, so pretty simple calculation here. Top of the fraction, you just need to do 0.3 minus 1, which is negative 0.7 molarity divided by 40 seconds. You just go into your calculator and then you do 0.7 divided by 40. And so the rate for the disappearance of A is going to be negative 0.0175 molarity per second. Okay, and this answer makes sense because it's negative, right? Negative means that it's going down, it's disappearing, which is exactly what A is doing. A is disappearing, so you want to have a negative rate. So for B, since B is appearing, it's going to have a positive rate, right? Okay, I know I went through that really fast, just kind of went boom, bam, 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 bam. But did you guys have any questions on any of the steps? Hopefully it's not too bad. Okay. Okay, so that's going to be the average rate. So how the rate of the reaction goes on average. Now there is something else called the instantaneous rate, and this one's a little bit harder to calculate if you guys don't do calculus. I'm not going to teach you guys how to do it with calculus, but instead we're just going to be looking at a chart in order to calculate it. So here we have this table that tells us the concentration of this compound right here at different periods of time. Okay, so let me zoom in a little bit more. So we have C4H9Cl, and we have the concentration at 0 seconds and then at intervals of 50 seconds. Okay. Now, what I want you guys to do is I want you guys to calculate the rate from the reaction rate from 0 seconds to 100 seconds. Okay. And I'm going to do the calculations for the reaction rate from 300 to 400. And we want to see if the rate is increasing or decreasing. Okay. Because rate is not always the same. It doesn't just automatically always go at that same rate. It's going to, want to change over time. Sometimes the rate will increase. Sometimes the rate will decrease. And we're going to be looking at this chart and looking at different points and see if the rate is increasing or decreasing. Okay. So basically do the same thing we just did with this table from 0 to 100. I'll do the 300 to 400, and then we'll calculate if the rate is increasing or decreasing. Okay. So take about 2 minutes to try that out. Isn't chemistry fun? You guys signed up for this, by the way. I tried to warn you. I didn't know you last year. So I'll give you guys maybe 40 seconds to finish up your rate calculations. I finished 300 to 400. So you guys can compare the two, and then you guys can get your final answer. Is it increasing or decreasing? Alrighty, guys. So if you guys are finishing up your calculations, please do so. But for the rate from 0 to 100 seconds, I got negative 0.00918 molarity per second. Did I do that correctly? Yes. Is that what you guys got? Okay. So this is the rate from 0 to 100. So the average rate from 0 to 100 seconds is negative 0.00918. The rate, though, from 300 to 400 is different, 0.000101. So is the rate decreasing or increasing? This is hard to tell, negative numbers, right? Okay, so if you look at this number, which number is bigger, the red one or the blue one?
But red. Less zeros on red.
Yes. So this is gonna be bigger. Okay, so the rate here was larger. So it was a larger rate, and then we have a smaller rate. So if we go from large to small, is it decreasing or increasing? Yeah, it's decreasing. The rate here is decreasing. Oh boy. I like how you guys can do all this algebra stuff, and then when we compare two numbers, it's like, what's going on? Yeah, so here, based on this data, we can see that, hey, in the beginning, this reaction was going a bit quicker, right? And as time goes on, it slows down. Yeah, what's up? Did I miss a zero? Really? Oh my gosh, Mr. O does not know what he's doing. Okay, so the final rate is 0.082 minus 0.1, right? And then divided by 100. Oh my goodness.
Yeah, I was looking.
I am like actually dumb, guys. Sorry, Mr. O was not doing too well when he made this answer key, I guess. How did I write a 9 for a 0? Anyway, yeah, same answer applies, right? Rate is going to be decreasing. Okay. Thank you, guys. I appreciate it. I think at this point, we all know I'm just making this up, just pretending like I know what's going on. Okay, so the point is, again, rate can change. Just because you have an average rate doesn't mean it's going to be the same, right? Averages within that average, different time intervals will have different rates. That's kind of the point that we're trying to get at. Yeah.
Oh no.
Oh, okay. Yeah. Okay, let's move on. So we are going to be combining reaction rates with your favorite thing in the world, stoichiometry. Okay. Okay, so there are many times when the rate for different compounds are not the same. Okay, what that means is if you have a reaction, sometimes for one of the compounds, the rate will be like 1 molarity per second. But for another one, it could be 2 molarity per second or 0.1 molarity per second. In the same reaction, different compounds will have a different rate or can have a different rate. Okay, so for example, we're looking at this reaction right here. We got this, right? This big thing. It's already balanced for you. But if you guys notice, if we just look at the reaction, we know already that for every 2 moles of N2O5 that disappears, there's going to be 4 moles of NO2 that appear and 1 mole of O2 that appears. So just by looking at the stoichiometry, right, we can already tell the rates are going to be different because if 2 of these guys disappear, 4 of these guys appear, and 1 of these guys appear, right? So the change is going to be different relative to one another. Okay, and so I want you guys to write this down. Now, you guys don't need to write this whole thing right here, but the important thing is that the rate is going to equal this equation right here. And if you guys notice, it's the same thing for all of the different compounds. Okay. So I'll break that down in just a second, but I want you guys to copy this equation down right here. The one in the pink box. Okay, so if we break down this equation, let's interpret what it means. Now we have this general equation right here. So the little letter is the coefficient in the front, and the big letter represents the chemical. You guys can see that, right, from the general formatting. Now, if we take a look at this equation, what we're saying is that the rate of change for one specific compound is -1 divided by the coefficient, right? And then whatever the concentration of the compound is. Now, the reactants, okay, I'm gonna do that in pink. The reactants have a negative rate, which makes sense, right? Because they're disappearing. But if you look at the products will have a positive rate because the products are being produced. And so if you notice the C and the D, they have a positive or they don't have a negative sign. So it'll be positive, but these guys right here will have a negative sign for their rate of change, okay? Okay, so basically, just do the regular rate equation, but just divide it by the coefficient, and that'll give you your rate. Yeah, what's up? Yeah, so just calculate like what we just did with the molarity on the top, time on the bottom, and then just divide it by the coefficient, and that'll give you the rate.
So like our average rate is like 0.5.
Mm-hmm.
The coefficient of 2 would be
0.5 divided by 2, correct, yeah. Yeah, so algebra is not too difficult. It's just kind of figuring out what the heck is going on here. Okay, so we'll do a practice problem right here. So let's say the rate of decomposition for this reaction right here. I have the reaction down here too. If we say that the rate of decomposition is 4.2 times 10 to the negative 7 molarity per second, what is the rate of appearance for these two? Now I'll do the NO2 with you, and then I'll let you guys do the O2 on your own, okay? So when you want to compare different rates, first thing you want to do is look at the rate that you are given. Okay, so the rate of disappearance for N2O5 will be 4.2 times 10 to the negative 7 molarity per second. Okay, now I'm going to specify the molarity by saying that it's for N2O5. Okay. So far, so good. Making sense? I'm just writing down the rate for that chemical. Now, I want to find the molarity or the rate of change for NO2. So this is actually very easy. All we need to do is a mole ratio. If we take a look at N2O5, the coefficient is 2, right? So for every 2 moles of N2O5, how many moles of NO2 are produced? What's the coefficient?
Oh, I know it's 4.
Yeah, 4. Yeah, it's going to be 4 moles of NO2. And these can cancel out. Now, if you want to see the actual algebra for that, it's because molarity is equal to moles over liters by seconds. So it would look like this. So the moles can cancel out. And then we'll get a new moles on the top right here from here. And so that's how the algebra works. But you can cancel those two out. And then that will give you your final rate for NO2. Okay, so super simple. You just have a mole ratio. Okay, so just to repeat what I just said, we write down the rate that is given to us. Okay, 4.2 times 10 to the 7 is the molarity or the rate change for N2O5. If we compare N2O5 with NO2, we see that the ratio is every time 2 moles of N2O5 disappears, 4 moles of NO2 appear. And so if we just do a ratio, we can see that the rate will be double. Okay. If we just do it with regular numbers, if I had 10 of these, okay, the ratio will be just double that because it's 2 to 4, 10 to 2. And so the rate is the same thing. Okay. So final rate, if I'm not wrong again, will be 8.4 times 10 to the negative 7 molarity per second. And that's going to be the rate of change for NO2. Any questions about that one? Yeah, what's up? Yeah, so if we break down this, I'm just going to look at the units of measurement, okay? So molarity is moles over liters, right? And then that's going to be all over seconds. Now, if we multiply it with moles over moles, okay? if we rearrange this right here, moles over liters divided by seconds, we can rearrange this as moles times seconds over liters, right? Because if you have a fraction divided by another fraction, you just need to bring this to the top. Okay, so that's where we get this. Now, moles can cancel out with moles, which is what we did right here. Moles cancel out with moles, but we're going to multiply it by different moles. And so it would just equal moles times seconds over liters, which is exactly what we started off with. And so that's why the rate is still molarity per second. So it's just basically it's just regular algebra where the units are canceling out with one another. But we just kind of skip that because it's kind of a pain to break it apart into moles over liters. And then we just divide it by moles. Yeah. Okay. Any questions? Other questions about this? All right, I want you guys to try the same thing for this reaction right here. Okay, you have 2 O3 or that produces 3 moles of O2. You got the rate, and I want you guys to find the opposing rate. What's that? Divided what by 2? No, you have the rate for O2, so you're looking for the rate of O3 here. Oh yeah, we could do that, but it's gonna be the same equation. You just change the mole ratio, so we're just gonna do 11.6. Yeah, my bad. I should have clarified. Thank you. Yeah, we're doing 11.6. My fault. Thanks, appreciate it. What? Alrighty, guys. I'm gonna start going over it. If you're finishing it, feel free to finish it up. I'll actually go through all the algebra and why we set up the mole ratio that we did here. Now, we just copied down the rate that we're given. It's 6 times 10 to the negative 5 molarities per second, and this is talking about O2's disappearance. Okay. Now, if O2 is disappearing, what do we need to specify? Actually, O2 is not disappearing, it's appearing, sorry. So O2 is appearing, so it's positive, my fault. Okay, so if we want to rewrite molarity right here, we can just rewrite molarity as moles over liters, okay? Now we can set up a fraction or a mole ratio. So I'm going to set up a mole ratio. Now we have O2 on the top, so I'm going to be comparing the moles of O2 with the moles of O3 because that's what I'm interested in finding. So the mole ratio is going to be 2 moles of O3 for every 3 moles of O2, okay? Now, the reason why, again, we can set up just a mole ratio is because we have moles on the top right here, right? This is talking about moles of O2. Okay. So what we can do is we can cancel out moles of O2 with moles of O2 because we got one on the top of the fraction, one on the bottom of the fraction. And then if we do the math, we just need to do 6 times 10 to the negative 5 times 2 divided by 3, which should give us 4 times 10 to the negative 5. Now, if you notice for the units of measurement, we're multiplying with moles of O3. So it'll be moles of O3 divided by liters, and then everything over seconds. And again, we can rewrite moles of O3 per liter. We can change this up into molarity, right? Moles over liters, and then molarity divided by seconds. So it'll be molarity O3 per second. And that's why we can use a regular mole ratio in order to get rid of the molarity. Yeah. Yeah, I was actually going to mention that. Dang, you got ahead. I was going to ask a trick question. So yeah, it is disappearing. So you will have to add a negative in front of it because it's the rate of disappearance. Good catch. Yeah, sig figs. Okay. All right, it's getting a lot more abstract now, right? You gotta, this is where your algebra really has to come into play, because if you have a very poor understanding of algebra, it's hard to kind of manipulate all these variables. We're gonna start looking at graphs soon, and so you're gonna have to be able to interpret them as well. Okay. Any questions about what we've talked about so far, though? Talked about rates, talked about comparing rates with stoichiometry. Okay, this next part is super duper important. It's called rate laws. Actually, I've been saying that like every single time, right? But yeah, this is all important. But rate laws, like this you need to know this to do your taxes, to drive to work, you know, to clean your car. Everything exists for rate laws. But anyway, this is important because it's going to carry over into the next 2 units. And that's why we're doing this rate stuff now. It's because the next unit, equilibrium, and the one after that, acid base, is all about rate laws. And so just make sure that if you have any questions, you ask me, because we need to get very comfortable writing rate laws, because this is kind of the foundation for the next 2 units, which are the biggest parts of the AP test. Again, about 60–70% of the questions come from the next 2 units, which is built on this right here. Okay, so the rate of the reaction depends on the reactant concentration, which is kind of obvious, right? Depending on how much you have in the beginning, that's going to determine the rate of the reaction. Okay, and this is represented by something called the rate law. Okay, and so for the general reaction, same thing as before, the rate law is going to be written like this. Make sure you copy this part down right here. So the general equation and the rate law, because that will tell you how to do it for every single reaction that we see. Okay. General reaction A plus B to C plus D. The rate law is just going to be the concentration of A, concentration of B times this K thing. We'll break this down in a second. All right, so I'm going to start breaking down this equation for you, just so that you guys have a general idea of what's going on. So if we want to find the rate law, it's going to be equal to this thing called K. Now, K is the rate constant, and it changes with temperature. Now, the key thing you guys want to notice, look at K, is the unit of measurement, because it's going to tell you the overall order. Now, I'll talk about that later in a sec, but K is just basically a constant that goes with every reaction. Every reaction at a certain temperature has a certain constant that's applied to it. What's important for the rate law is the concentration to the molarity of A and the molarity of B. So if you guys notice, the rate law is going to depend on the reactant concentrations, how much you have in the beginning. It doesn't really matter what the concentration of the products are. And then we have M and N right here. And these are going to be small whole numbers. Okay, and we'll elaborate on this in just a second, but this is all going to connect to something called reaction orders. Okay. So that's basically what this equation means. Okay, so what we're going to be doing first is we're going to be looking at some sample pieces of data, and we're going to be learning how to calculate K. So if you guys are decent with algebra, which you guys are, this shouldn't be too difficult. We're just going to be using this equation right here. Okay. All right, so we're going to do 11.7. And we have this equation right here, and we have a lot of information right here. Okay, so I'll give you guys a second to just look at the information. But what we want to find out is I want you guys, we're going to do part A. I want you guys to take about 3-4 minutes to look at the data. But I want you guys to calculate the value of K, right, from the rate law that we looked at earlier for experiment 1. So experiment 1 is right here. And I want you guys to use that equation we just had. Rate is equal to K, and then the concentrations, in order to calculate K for experiment 1. Okay, so take a second to look at just the data, look at the equation, just try it out. Just take some time to experiment and see if you can figure out the value of K. See if you can get the unit of measurement as well. Oh, one thing I forgot to mention, the M and N is usually going to be the coefficient in front of that compound. So M is going to be the coefficient for A, and N is going to be the coefficient for B. Sorry, I forgot to mention that. Mm-hmm. So if it's a 2, you would square the concentration. All right, guys, if you guys are still working on it, feel free to finish up, but I'm going to just start going over it for the sake of time. So What we're going to be looking at is we're going to be calculating the value of K for experiment 1. Okay. So I'm going to cover up everything else because everything else is not that important right now. We're just going to be looking at experiment 1. Now we know that for the rate law, the rate is going to be equal to K. Okay. And then the concentration of one of the reactants, which is going to be NH4 plus ammonium. The coefficient is 1, so we can just put to the power of 1. That's going to be our M. The coefficient of NO2 minus, which is also going to be 1. And so this is our rate law for this reaction. Okay. Basically, we just took the reactants and put the concentrations there. Now, we're trying to find K. So what we can do is we can rearrange this equation, right? If I wanted to isolate K, I could divide by the two concentrations, and I can get the rate divided by the concentration of ammonium and the concentration of NO2 minus. Okay. And then from there, we just need to plug in the values that we have. We said that the rate is 5.4 times 10 to the negative 7. So I'm going to write 5.4 times 10 to the negative 7, and it's going to be molarity per second. So molarity per second divided by the concentration of NH4 plus, which is 0.01. So 0.01 molarity. We got NO2 minus, which is 0.2. So 0.2 molarity. And then so from here, we can cancel out the molarity with the molarities on the bottom. Right? I'm messing up. No, just one of the molarities, sorry. Because one of the molarities will cancel out. And then from here, we can just do the math for this calculations. Might be easier if you have a graphing calculator or more a better scientific calculator. But the bottom of the equation is going to be 0.01 times 0.2. So the bottom is going to become 0.002. And then I'm going to do m negative 1 just to show that it's on the bottom of the fraction. And then we have 5.4 times 10 to the negative 7. So we have 5.4, and then we're going to have to divide that by 0.002. And so we have 2,700. So it's going to be 2,700 times 10 to the negative 7. And then we got rid of the molarity. So it's going to be seconds negative 1. And then we could bring up molarity negative 1. And then we need to put this in scientific notation. So we just move the decimal over 3 times to the left. And so that's going to be 2.7. And then that's going to cause our exponent to go up. So it's going to be negative 4. And so your final answer will be molar 2.7 times 10 to the negative 4, molarity negative 1, seconds negative 1. And that's going to be your unit of measurement for the rate constant. So not too difficult to plug in, but the math can get a little bit complicated, especially with the units of measurement, right? Because now you have molarity on the bottom, seconds on the bottom. And so just make sure you're keeping track of where your units go. The algebra gets a bit tougher going forward. Okay. Anyone able to get this on their own? Yeah, good, good. Including the units? Okay, units were tough. But if you got 2.7 times 10 to the negative 4, that's all good. We're good for now. Okay. So this is going to be the answer for A. I want you guys to try B now on your own, okay? Okay, I want you to do the same thing for experiment number 3. And I want you guys, again, try to get the units of measurement as well, okay? Try to get comfortable figuring out where the molarity, where the seconds go, and how to express that. I'll give you guys another minute to finish experiment 3. Alrighty, guys, I'm gonna start going over experiment 3. If you're finishing up, feel free to do so. But for the sake of time, we'll go over experiment 3. Okay, basically the same thing as before. We can rearrange the rate law equation to have rate on the top, and then we're gonna divide by the concentration of ammonium and nitrite. Okay, so we know here that the rate is going to be 21.5 times 10 to the negative 7, and it's going to be molarity per second. And then we have the concentration of ammonium, which is 0.04 molarity. And then the concentration of nitrite is 0.2 molarity. Okay, and then we can do some bookkeeping with the units. Molarity is going to cancel out with one of the molarities on the bottom. So we know that automatically we're going to end up with the same units of measurement. Molarity is on the bottom, so I can do -1. And then seconds is also on the bottom of a fraction, so it's also going to be -1. So now we just need to do the calculations for the numbers. Okay, for the bottom of the fraction, we're going to do 0.04 times 0.2, which is going to be 0.008, so 0.008. And so what we have to do is just go to 21.5 divided by 0.008. That's going to give us 2687.5 times 10 to the negative 7. But since we need to move the decimal 3 times to the left, same thing, we're going to end up with 2.68. I'm going to round it up to 8 times 10 to the negative 4. Okay. And then this is going to be your final answer. So the K value for experiment 3 will be 2.688 times 10 to the negative 4 molarity, or per molarity per second. Yeah. Sorry, what was that?
Could the units be liters over seconds?
Liters over seconds times, and then moles on the bottom as well. Yeah, but you want to keep it in molarity, and so this is just a general way of writing. But yeah, you are correct. Yeah. I would keep more units of measurement. We didn't talk about significant figures just because we didn't have time to do it. So I always recommend 3 non-zero numbers after the decimal, just to be safe. Okay, so now we're going to go on to the last part of this problem. So I have the K for experiment 1 right here, what we just did. And then we have the K for experiment 2 or 3. So what I want you guys to do now is I want you guys to see if you guys can figure out the pattern. Does changing the initial concentration of reactants affect the rate and the rate constant? How does it change it? Okay, so what I mean by that is we have the K value for experiment 1 and we have the K value for experiment 3, right? If I could ever get this to erase. Okay, so experiment 3 was 2.688 times 10 to the negative 4. Okay, I want you guys to see if you guys can see the pattern. As we change the concentration of reactants, how does that affect rate and how does that affect K? So see if you guys can just write a sentence, very concise, very brief, explaining how changing the reaction concentration will affect rate and affect K. After that, we'll take a break, okay? Okay, keep it short. Shouldn't be more than 2 sentences tops. 30 seconds to finish up your explanation. Again, you shouldn't be writing very much. Alrighty, guys, let's finish up this problem and then we will be done. Okay, so biggest thing we want to figure out is we want to compare the numbers, and that way we can talk about the trend. Okay, so if we look at experiment 1 and 3, let's look at the reactant concentration because that's what we're asking. We're being asked to look at. So if you look at the concentration of ammonium, did the concentration go up or down? Dude, decimals are so hard, huh? Yeah, it went up. Yeah, so it increased. No, it's okay. Not a big deal. And if you look at the concentration of NO2 minus, it stayed the same, right? So we can ignore this. This isn't very important. It stayed constant. Okay, now let's look at the rate. So if we look at the rate, difference in rates between 1 and 3, did the rate increase or decrease? Yeah, it increased. Okay. Which is why they didn't do it in scientific notation. Easier to look at if we have the same exponent, right? Okay, so we can actually write the first part of our sentence or our explanation right here. We can say that as the reactant, man, thinking of donkeys. As the reactant concentration increases, what happens to the rate? Rate increases. Okay. Very simple correlation that you guys can see, right? Now let's look at the K value. For the constant, did the number increase or did it decrease? It decreased. Because if you look at it, if we just ignore the times 10 to the negative 4, right? What's bigger, 2.7 or 2.688? Yeah, 2.7 is bigger than 2.688. Dang, Josh, you want to go back to kindergarten? Yeah. No, I'm just playing. No, it's tough, especially when there's exponents and decimals, and then we got negatives in there too. It's tough. It's tough to keep track of all this. I still make mistakes when I look at this. So yeah, 2.7 is greater. So what happens to the K value? K value decreases, right? So we can say as the reactant concentration increases, the rate increases, and the rate constant decreases. Okay, there you go. So should have answered in one sentence. I said 2 sentences if you split that up, but it shouldn't be very long. Yeah.
It's because the temperature starts increasing as reaction rates occur. Because like
No, there's no change in temperature. Everything here is at 25 degrees Celsius. Yeah. So if you, is that the end of your question? Okay, my fault. I thought you were gonna say something. All right. Let's take a quick 5-minute break, and then we'll come back, and then we'll end with the last topic for today. Okay. Okay. Let's move on. So we're gonna move on, and we're gonna be talking about something called reaction orders. Now, I vaguely touched on this a little bit earlier, but for reaction orders, what you need to know is that you see M and N, right? These exponents. When you add them up together, the number that you get is going to be your reaction order. Okay. So for us in our previous example, it was 1 and 1, right? This is the reaction that we did earlier. The exponents were 1 and 1. So if we do 1 plus 1, what do we get? 2, yeah, genius. Case 2. So that means this reaction right here is called a second order reaction. Okay, super easy to figure it out. Just whatever m plus n is, that is going to be our reaction order. Okay. So far making sense? How to find the reaction order is just m plus n. So let me quiz you guys. What if our exponent here was 2 and 1? What would be the reaction order? Yeah, third, right? What if the exponents were 0 and 0? No, there is a reaction still. It's going to be a 0 order reaction. Yeah. Okay. So literally just add up m and n, and that's going to tell you what reaction order is. Usually, for AP Chem, you'll see 0, 1, 2, maybe 3, and then if they really hate you that year, 4. But usually we won't go. It doesn't go any higher than that. Like it's gonna stick to 0, 1, and 2 like 99% of the time. Yeah. What's up? We'll talk about that in a sec, or probably next time. But it's usually when the rate is independent of the reactant concentration, because if it's 0, it's 1, right? So it's just going to depend on the constant, not the concentrations. Yeah, good question though. Okay, so that's how you find reaction order. Just add m and n. Okay. And here we have some examples. If you take a look at this first one, what is the reaction order? Okay, show me with your fingers. I'm going to cover the answers. For the first one, what's the reaction order? Fingers. Reaction order. The first one. It's going to be 1. Because we're not looking at the coefficients, we're looking at the rate law. What number is up here? I know, this is tough. Now you're going to change your answer to that one. Okay, yeah, so the reaction order for the first one is 1. It's a first order reaction. Okay, what about the second one? What's the reaction order? You can't really do it with your fingers, but yeah, like this, right? 1.5, right? Using a cross. Yeah, so this one, the reaction order will be 1.5. So you can have a 0.5 order reaction. And then what about for the second one? This one you could do with your fingers. Dang, you guys are getting all shy now. Okay, so what's the exponent for H2? 1. What's the exponent for I2? Okay, so what's the rate order, reaction order? 2. Yeah, there you go. It's okay, guys. If you're gonna be wrong, just be loud and wrong. And if you really don't like this, just okay. So that's gonna be the answers: 1, 1.5, and 2. Okay, that's how you do it. You just need to add up the m and the n. It doesn't matter what the coefficients are. Earlier I kind of mentioned it briefly too, but I said usually it's going to be the coefficients, but as you can see here, it's not always going to be the coefficients. So don't assume it's going to be the coefficients. Always if they give you the rate law like this, okay? Okay, so we have this chart right here, and we're not going to be doing a problem with this chart, but I want you guys to just analyze this chart real quick. Okay, I'm going to explain a couple things about it. Now, if we have an equation like this and we have the rate law, okay? Now, what we're gonna be analyzing this a little bit, and I want you guys to just look at these points here on the bottom, okay? Okay, so the exponents m and n in a rate law, it indicates how the rate is affected by each reactant concentration, which makes sense, right? Because if m right here is going to be, I don't know, like 2, right? That means you're gonna be squaring whatever the concentration is in the middle, right? So the higher the exponent value, the more the reaction rate is going to change depending on that reaction. So basically, the bigger the exponent, the more power that reactant has over the reaction rate, okay? Okay, so that's the first part. So here, the rate at which NH4 plus reacts with NO2 minus, it depends on NH4 plus raised to the first power. That was the reaction that we looked at earlier. Okay, and so that's basically what it's trying to tell you right here. Depending on what the exponent is, it's going to affect the rate because it's going to affect the reactant concentration that we are given. Okay, so basically, the bigger the exponent, the prettier the person is. Okay, it's going to affect the rate of attraction a lot more. Okay, but the smaller the number, the less it's going to affect the reaction rate. Okay. Okay, so moving on. If the reaction is second order and it's the concentration of A is squared, then doubling the concentration is going to cause the reaction rate to quadruple, right? Because if we have like this, if we have rate is equal to concentration of A and it's squared, if the concentration is 2, then the rate is gonna times 4 because you need a square, right? If the reaction rate is if the concentration is 3, it's gonna cause the reaction to go up by times 9. No, I don't want to buy this. How do I go back to normal? Yes, there we go. Okay, because if it's 3, then it's gonna go to times 9. Okay, so just keep that in mind that the exponent is gonna change the rate because you need to, do the exponent for the concentration. Okay, so we'll start nice and easy with the problems, and we'll end with this one, 11.8. Okay, so for this reaction, A plus B is C. The rate law is going to be this right here. Okay, each of the boxes represents a reaction mixture where A is the red spheres and B are the purple ones. Rank these in order of increasing rate of reaction. Okay, so I'm going to do the first one for you, and hopefully that'll help you guys figure out 2 and 3. Okay, so I'm going to copy down the rate law that we have in the problem. The rate law is K, concentration of A, concentration of B squared. And then we're going to apply this to reaction number 1. Okay. Now, before we do that, let's just for practice, what's the rate order? The reaction order. Yeah, 3. Yeah, west side, right? Third order. Okay, because it's 1 plus 2. Now, so for equation or for example 1, box 1, let's just plug in the values. The rate is going to equal K. The concentration of A is the red balls. How many red balls are in there? 5. Okay, how many blue balls are in there? Or purple balls? 1, 2, 3, 4, 5. Yeah, 5. Is that blue or purple? I can't even tell. Purple? Okay, it looks blue to me. Okay, so it's gonna be this right here. So we have the rate for the first box is gonna be K times 5 times 5 squared. 5 squared is 25 times 5 is 125. So the rate for box number 1 is going to be 125K. Okay, so box 1 is going to be 125K. So I want you guys to do the same thing. You could work with the person next to you to split it up. I want you guys to find the rate for box number 2 and box number 3, and I want you guys to figure out which one has the highest rate of the reaction. Okay.
Even said that in the problem is purple.
Oh. Yes. But I'm just looking at the colors and it looks blue to me. Alrighty, guys, I'm gonna start going over it. If you're finishing up, feel free to finish up, but let's finish it. Okay, so the rate for 2 is going to be K times, what's the concentration of A? 7. Concentration of B? 3. going to square it. And so you'll have 7 times 9, which will be 63K. Okay, we're going to move on to reaction 3. The rate is going to equal K times 3 for A, and then 7. Thank you. 7 squared. And so your rate will be 147K. Okay, so which one of these has the greatest rate of reaction? Yeah, 3 is going to have the greatest rate of reaction. Now, the reason we're going over this is so that you guys can see how the rate of the reaction is affected by the exponents. If you guys notice here, we had a lot of A, right? We had 7 for the concentration of A, but it doesn't change the rate of reaction. Why? Because it doesn't have an exponent, right? What this is showing us is that in some reactions, certain compounds have a greater effect on the rate, okay? Because even though we had a lot of red, it's not going to change the rate very much because it's not dependent on A to run the reaction. Whereas here, for number 1, we had an equal amount, and it's going to be a higher value than if we had more red. So blue has a much higher effect on the rate of reaction than red does, just because of the rate law, okay? Just keep that in mind. Basically, it sums down to some chemicals affect the rate more than others. That's how we can basically sum up this whole rate order stuff, okay? So we'll finish it off there for now. Make sure you guys keep up with your reading, and I would recommend that you guys start your homework tonight if you guys get a chance, because it will be due at the end of this week, and it is kind of long, okay? Yeah.